Welcome to SpectraGuru, your AI-powered Raman spectroscopy analysis tool. This video is the second of a two-part series demonstrating the processing features of SpectraGuru. To begin, click Start. From here we will upload our spectra, a process covered in detail in the previous tutorial video. Navigate to the processing page, then click Plot. We start with the smoothing feature. Begin with the default settings of our Savitsky-Golay filter, which lets us control balance between signal fidelity and smoothness, a technique used in spectral processing to reduce noise and enhance readability of the signal by averaging adjacent data points. This helps us gain a clearer representation of the spectral data. At your discretion, increase polynomial order to reintroduce signal or decrease polynomial order to maximize smoothness. For the 1D fast Fourier transform, here we smooth the signal by filtering high-frequency components via Fourier domain. Choose 3 edge treatments. Mirror, best for preserving boundary continuity. Edge, less aggressive but maintains original edge behavior. Or Zero, which applies hard cutoffs at signal edges. Be cautious not to over-smooth. Too much filtering may remove meaningful spectral data, as seen in these final 2 examples. We now move on to baseline removal. One approach for dealing with unwanted background signal is baseline correction, which helps isolate true spectral peaks by removing fluorescence, drift, or scattering artifacts. We begin with our AIR-PLS approach. This stands for Adaptive Iteratively Reweighted Penalized Least Squares. This is a smart automated method that fits the baseline by penalizing curvature, then adapts based on the residual. This is ideal when you don't know what the baseline should look like. We explore several parameterizations here. This approach may or may not be best depending on your needs, but multiple parameter explorations can be attempted without permanently altering your spectral data. As we've seen, each pre-processing step offers flexibility but also transparency. You always see what's being applied and you control the outcome. If need be, just reparameterize and try again. Our second approach is the mod poly feature, which is modified polynomial fitting. This method fits a polynomial baseline to the data. Lower orders remove simple drifts while higher orders capture more complex curvature. Be careful with higher orders, overfitting can distort your spectrum. Our third approach is Gaussian-Lorentzian fitting. This fits the baseline using broad Gaussian or Lorentzian curves, often used in biological or surface-enhanced spectra. This feature allows us to set different ranges for spectral analysis. Let's try range 1 from 400 to 1200, range 2 from 1500 to 2200. After applying the ranges, click Process. We see that our settings leave an unprocessed region from 1200 to 1500 on the x-axis. This is especially useful for SIRS, where background fluorescence is not flat. Make sure to be careful with parameterization so you don't overly smooth your signal. Additionally, be sure that the parameter ranges you set don't clip any values for which you desire processed analysis. Normalization helps standardize spectra for comparison, visualization, or multivariate analysis. We begin with normalizing by area. This scales the entire spectrum so the area under the curve equals 1. This is useful when comparing signals of different intensities but similar shape. Next, we normalize by peak. This scales the spectrum so the maximum peak equals 1. This emphasizes relative peak height across spectra. And lastly, we have min-max normalization, which adjusts the spectrum so values range from 0 to 1 and is handy when plotting multiple spectra on the same scale. Our fourth feature for this video is outlier removal. We'll explore outlier removal with an uploaded spectra. Outliers can mask patterns or throw off downstream analysis. Our earlier detection model uses statistical filtering across spectra. But it's not one size fits all, so we're not using our sample spectra data here. The default settings are 4, 6, 4, but they may not always flag the correct data. For better results on this particular spectra, let's try adjusting to 4, 1.7, 6. This shows we can't blindly rely on the default settings, but rather use them as baselines to explore the sensitivity and tune the parameters as needed. Thanks for using SpectraGuru for your Raman and SIRS based research and work.